Here's another equality with binomial coefficients, which I'm mostly showing for its proof. The proof has a nice idea. The equality says the following: let n be a non-negative integer, prove that this sum is 2 to the n. This appears in Engel's book even twice with two different proofs, so there's a lot to learn from it. So what's the first thing you see? You cannot directly prove this by double counting because these are not integers. They don't count anything. And no, this is not going to be an integer even if you multiply it with n plus k choose k. However, the sum is an integer. But counting gives you integers, but some other things give you rational numbers or even real numbers. One of those other things is probabilities. In a sense, probabilities really are counting, but because it's a number of something divided by the total number of outcomes. But it's often easier to think in terms of probabilities. So what probabilities are we talking about? Well, let us toss a coin, a fair coin to be precise, 2n plus 1 times. So let h be the event the coin comes up heads at least n plus 1 times. Let t be the event the coin comes up tails at least n plus 1 times. So a typical outcome would be if 2n plus 1 is 5, an outcome is ht, hht, for example. Heads, tails, heads, heads, tails. And in this case, you are in the event h, because h appears at least 3 times. Basically, h is saying the majority of times you have heads, and t says most of the time you have tails. So the probability of h plus the probability of t is 1, because h and t are complementary events. If you have one, you don't have the other. All right, now let's actually compute the probabilities. So let's start with probability of h. Okay, how to compute the probability of h? How to compute the probability that most of the times we will have h? One way is the following. For each k in 0, 1 up to n, we define the event hk, which is a stronger version of h. It's namely the coin comes up heads at least n plus 1 times. Furthermore, and by the n plus first time it comes up heads, it has come up tails exactly k times. So this is a bit of a mouthful. Basically, if the coin comes up heads at least n plus 1 times, there is a certain time at which this becomes clear, namely the n plus first time when it comes up heads. From that time on, it doesn't matter what else. You can basically stop throwing. You can stop tossing the coin. You've already decided whether you have h or t. And if by that point it has come up tails exactly k times, then you say you're in the event hk. So for example, hht is in h1 because heads comes up 3 times, which is at least 3 times. And by the third time, it has come up tails exactly once. For another example, let's do 2n plus 1 is 7. Is that right? No, that's right. So this is, wait, is this right? No. Something's wrong. 1, 2, 3, 4, 5, 6, 7. Combinatorics and counting, as you see, are two different things, at least two different skills. So this was 2n plus 1 is 5. This is 2n plus 1 is 7. So here we are in event h because heads comes up 4 times. By the fourth time it has come up, tails have happened 3 times. So this is an h3. And just as another example, which h is this? So heads comes up 5 times, which is at least 4 times. So you're in h, but which h? Well, by the fourth time heads has come up, you have had only one tails, so h1. It doesn't matter that you have a tails afterwards. The tails doesn't matter anymore. Oh, and I should mark this h as the fourth h. All right, so we have the probability of h is the probability of h0 plus the probability of h1 plus and so on plus the probability of hn. Because h is a disjoint union, now I'm talking of events as sets of this h0 up to hn. Why is that? So h means that the coin comes up heads at least n+1 times, and if you know that this is happening, you can measure how often it has come up tails before. And that number must be between 0 and n. It cannot be n+1 because that would we don't toss it that often. It would be 2n+2 in total. Okay, so can we now compute each of these little probabilities? Yes, we can. Namely, for each k, we have, and now I'm just going to restate this event. You're going to see in a moment. The first n plus k tosses of the coin lead to tails exactly k times. And the next toss leads to heads. Or so let me restate it. The first n plus k times you toss the coin, it comes up tails exactly k times. And secondly, the next, so the n plus k plus first time, it comes up heads. Why is this the same? You can convince yourself that it's the same, because if this is true, then among the first n plus k plus 1 times, it comes up heads n+1 times, so the coin comes up heads at least n+1 times, and by the n plus first time it comes up heads, it has come up tails exactly k times. So this is a fairly easy verification that this is really the same statement. So now this restatement has a nice property. It's so you're tossing the coin, the tosses are independent. The coin has no memory. And since this condition and this condition talk about different tosses, you can just say that the probabilities just get multiplied. So probability of this part times the probability of this part. Okay, now this is easy. This is just 1/2 because it's a single toss. It comes up heads with probability 1/2. It's a fair coin. Now this is a counting question. You're tossing the coin n plus k times, so there is altogether 2 to the n plus k possible outcomes. But how many of them have the properties that the coin comes up tails k times? I claim that it's n plus k choose k, because there is n plus k possible, so there is n plus k tosses. You have to choose which k of them will give you tails. The rest will come up heads. And the number of choices is just a k element subset of n plus k, so it's n plus k choose k. And now you just plug these things in and multiply. Okay, so coming back to this equation, let me rewrite it with the sum sign. And the probability of hk, we have just computed. It is this beast. So you have this sum here. And I'm going to message it a little bit. The 1/2 can go forward as a factor. And I also can rewrite this 2 to the n plus k is 2 to the n times 2 to the k, and the 2 to the n can also go to the front because it doesn't depend on k. There, we have a formula for probability of h. Similarly, probability of t is the same. Why is it the same? Because the coin is fair. The heads and tails are behaving the same way. Now recall that the probabilities add up to 1. So in light of the last two equations, in light of this explicit formulas for these probabilities, this rewrites as this plus this equals 1. And now you can simplify, because these two terms are the same. So instead of summing this thing to itself, you just multiply it by 2. Now we can, of course, simplify this further. Instead of dividing by 2 and multiplying it by 2, so I just cancel the 2 here. And of course, I can bring the 2 to the n on the right-hand side. And this denominator, I can write it as a fraction. Sorry, I can just rewrite it in this way. I brought this 2 to the k here. And this is what we wanted to prove. This is by far not the only possible proof of this fact. In particular, there are proofs by induction. There is different proofs using algebra, but this is an example, a prime example of a probabilistic proof. Even if you can restate it in terms of counting, it's kind of easier to think of it in terms of probabilities. So this is an example of a binomial identity, so an identity with binomial coefficients. And as you have now seen, there is a lot of strategies that can help you prove such identities. This was just one of them. This kind of polynomial identity trick was another. Here we've seen a bunch more, and a lot more you can see on the current homework set.